Welcome back, everyone. In this video, we're going to go over a bunch of examples of using proof by induction. So as the first example, let's see what happens if you add the first n odd numbers. Well, it's not too hard to guess. If you look at the first sum of the first two would be 4, the first 3 would be 9, and then the first 4 would be 16. And so it's not so hard to guess that the answer is n squared. So let's prove this always works, that if you add the first n positive odd numbers, you always get n squared. So of course we're going to use induction, which means, again, that we have two different pieces that we have to put together. So we have to show the base case, which is namely we have to show this is true when n equals 1. Well, what does this say when n equals 1? When n equals 1, this literally says 1 equals 1. So that's great. And then we have the inductive step. This is usually the more challenging part. We have to show that if the sum of the first k odd numbers is k squared, then the sum of the first k plus 1 odd numbers is k plus 1 squared. Note, everything here only even makes sense for n a positive integer, so just sort of ambiently floating over here, n and k are positive integers. So remember, this is an if-then statement that we need to prove, so we can do the proof within the proof. And so we'll suppose the if part here, that is, we'll suppose k is a positive integer, and the sum of the first k odd numbers is k squared. And this part, the if part of this, is what we call the inductive hypothesis. So we're assuming the inductive hypothesis or whatever here. It's the if part of this statement. And so now we want to look at what happens when we look at this thing over here on the left-hand side. And like in the last video, I'm going to start by rewriting this thing so that it looks more like that. I'm also going to stop writing this like this and start writing it as 2k plus 1. Now, I want to reiterate, if you're trying to prove an equality, you absolutely cannot write down the equality in order to prove it. You have to start with one side of the equality and work until you get to the other side. So, I have not gotten anywhere near a k plus 1 squared yet. I've not written that down as part of my proof. I'm hoping that over time, this thing will turn into k plus 1 squared sort of on its own. Okay, so this is the thing that we assumed was k squared. So this equality now is k squared plus 2k plus 1 by the inductive hypothesis. In other words, by that thing we assumed when we were proving this if-then statement. But now we're almost done, because that is k plus 1 squared. And so once we've written that, we've now shown that as soon as this statement is true for some integer, it's true for the next integer. And then the next one, and then the next one, and then the next one. And since it's true for 1, then it's true for 2, 3, 4, 5, and so on forever. And so it's true for all the integers, and so we've completed both pieces of induction, so we get to put a little proof box, and then go on to another example. Now, this particular example is a pretty beautiful demonstration of both the pros and the cons of induction. So what's the pro? Well, the pro is that we were able to guess this formula just by looking at a tiny bit of data. This 1 is 1, 1 plus 3 is 4, 1 plus 3 plus 5 is 9. And so once we'd guessed the formula, induction made it easy to prove. So this is a very big pro. And this is a very common theme that you'll find in mathematics, is that a lot of times you don't need someone to tell you what the formula is. You can look at a few terms, guess, and then induction gives you an almost algorithmic way to write down a proof of that claim. Indeed, you might have felt throughout this course as though this doesn't sort of feel like math because there's not any real, rules or structure or algorithms to follow. It's much more freeform and creative. Induction is not that creative. Induction basically gives you an exact template, and then you can follow the template in order to get a proof. I mean, presuming the thing is true, of course. So that's a huge pro. Induction lets you verify formulas that you think are correct pretty easily. However, implicit in this statement are sort of two cons. One con is that you have to know the formula before you can prove it. Now, arguably all proof methods suffer from the property that you need to know what's true in order to prove it, because you need to know what it is you're trying to prove. But induction suffers this much more than other proof methods. You can start trying to write down a direct proof of something, sort of play with how the pieces fit together, and maybe you can discover new things just by doing that. With induction, if you don't know what the answer is, you get nothing. There is nothing you can do to sort of work out what the true thing is using induction itself. The second con to induction is that induction doesn't really give you a great sense of why things are true, at least in my opinion. Now, we've talked about this a little bit before, but it's worth restating. Not all proofs are created equal. And it's not the case that some proofs are better than others. I mean, maybe that is the case. But more to the point, different proofs have different strengths. And so proofs by induction are strong in terms of sort of ease of use and shortness of proof. Whereas proofs by induction tend to be less strong in terms of explaining why some fundamental fact that you want to understand is true. So let's just take, for example, the thing we just proved, which says, among other things, that this is supposed to be 36. And on the one hand, well, that's not super profound. You could just add the numbers together. But you could ask, like, why is this number a square? And, well, basically the proof by induction can be summarized because it is, or if you want to be slightly less terse, it's true because once it's true, it keeps being true. But I think I can draw you a picture that will actually make this much clearer. And so what am I doing here? I'm drawing 36 dots, but I'm drawing them in a very suggestive way. So here was the first dot, then here were 3 more dots that I sort of wrapped around that dot so that it made a 2x2 square. And then I was able to wrap 5 dots around that so that it turned it into a 3x3 square. Likewise here, I wrapped 7 dots around this to make this a 4x4 square. And so you can see where this is going. So there is my 9 dots, and then here is my 11 dots. Now, a picture is not a proof, but I feel like I learn a lot more about why this thing is true by looking at this picture than I do by looking at our proof by induction. That's maybe a bit of personal taste, but that's how I feel about it. So here's a new question. Let's prove that for all integers greater than or equal to 7, n factorial is greater than or equal to 3 to the n. Now, if you're particularly astute, you might notice that I said induction problems typically are about the positive integers, whereas this problem is about the integers that are greater than or equal to 7. But if you think about the picture I drew of induction, it sort of started with one lily pad, and then the frog sort of hopped along to the next, and the next, and the next, and the next along the way. And in original induction, this was 1, then 2, then 3, then 4, then 5. Well, I could draw exactly the same picture with 7, then 8, then 9, then 10, then 11, and so on. And so the only thing that's going to be different here versus our previous examples is that we're going to have to choose a different base case. Namely, in this instance, I'm going to choose n equals 7 as my base case. So it's important not only that you understand the outline of induction, but we're also going to talk about a variety of ways in which you might tweak the outline of induction to prove things that you couldn't prove with the exact outline that I gave you. So we proceed by induction. Okay, again, we're expecting here a base case and an inductive step. My base case here is going to be n equals 7. And so for n equals 7, I need to check that 7 factorial is greater than or equal to 3 to the 7th. So for this base case, I actually really have to check something. Namely, I need to check that for n equals 7, we get 7 factorial is 5040, and 3 to the 7th is 2187, and so, as claimed, 7 factorial is greater than or equal to 3 to the 7th. This is the first time for the base case we've actually had to check something. So now what's our inductive step going to say this time? It's going to say that if I take an integer that's greater than or equal to 7, and it happens to be true for that integer, that k factorial is greater than or equal to 3 to the k, then the same is true for k plus 1, namely k plus 1 factorial is greater than or equal to 3 to the k plus 1. So we start our proof as you would expect. Suppose k is an integer that's greater than or equal to 7, and k factorial is greater than or equal to 3 to the k. Now, how are we going to get from here to here? And this is where I think it is really helpful to pull out scratch paper. And so what we have is that k factorial is greater than or equal to 3 to the k. And what we want is that k plus 1 factorial is greater than or equal to 3 to the k plus 1. In all of our previous examples, the key was to relate part of this thing back to the original. So I need to think about sort of like how I can pull this thing apart to make it look like our original inequality. And so how are k plus 1 factorial and k factorial related? Well, if you took Calc 2 recently, you probably had to do a bunch of ratio test examples where you had to remember that k plus 1 factorial is the same thing as k plus 1 times k factorial. And 3 to the k plus 1, that's the same thing as 3 times 3 to the k. And so what I want to point out is that our original pieces have appeared. There's a k factorial. There's a 3 to the k. And so what sort of happened here is that somehow we've sort of, like, quote-unquote, multiplied this inequality by k plus 1 is greater than or equal to 3, I guess? That is to say, if I just multiplied these two inequalities together, I guess I would just get that, which would give me that. Now, why did I have to do this on scratch paper? Well, the reason is because in order to write this down and sort of uncover this relationship I was looking for, I needed to first write down the thing I'm trying to prove, namely this inequality. And then I manipulated it. And so I was really here working backwards, right? Because I started where I need to finish. Now, that can be very useful, and indeed it sort of led to us finding the proof, but when we actually go to write the proof, we're going to need to write it this way, rather than the way we actually discovered it. So bear this in mind. When you want to work backwards, you want to do that on scratch paper, and then you want to write the proof forwards. So let's go back to writing this down now. So I'm going to start by saying, since k we know is at least 7, k plus 1 is at least 3. Now, if I'd have written this down immediately after this without any commentary, it would have looked like a very weird thing to say. But because of our scratch work, we actually can make sense of this. We actually know that that's the thing I need. And so I'm going to be able to get to the conclusion of my inductive step. Namely, both of these are true inequalities of positive numbers, and so we're allowed to multiply them together and still get a true inequality. Remember, you have to be very careful when you want to multiply inequalities by anything that could plausibly involve a negative number, because negatives actually flip inequalities. But factorials and powers both happen to be universally positive, so I don't have to worry about that. So, since everything involved is positive, we can multiply the inequalities together, which will give us k plus 1 times k factorial is greater than or equal to 3 times 3 to the k, and then using how factorials work, that's k plus 1 factorial, and using how exponents work, that's 3 to the k plus 1. And that, what do you know it, is exactly the thing that we were trying to prove. And that means we've completed the inductive step, and so together with the base case, this actually works. And we're done. This proof is an example of one where I think the proof by induction actually does a really good job of explaining what's happening with this inequality. Namely, when we go to up the input by 1, that is, when we go from n factorial to n plus 1 factorial, and 3 to the n to 3 to the n plus 1, we on the one hand are multiplying by n plus 1, and on the other side by 3, and so once n plus 1 is bigger than 3, that means I'm making the left-hand side more bigger than I'm making the right-hand side. But that observation by itself isn't quite enough to complete the proof, because if the right-hand side happens to be bigger than the left-hand side, then the fact that the left-hand side gets bigger faster than the right-hand side doesn't actually tell me that the left-hand side is bigger than the right-hand side. But what I definitely know is that as soon as the left-hand side is bigger than the right-hand side, it will stay that way forever, because every time I take a step forward, I'll be increasing the left side by more than the right side, so as long as the left side's already bigger, then I will never get to a point where the power of 3 is again bigger than the factorial. And so a key piece of the proof really is this base case where I check that by n equals 7, it has happened that the factorial has eclipsed the power of 3. You can check, though, that, for example, for something like n equals 4, n factorial is only 24, whereas 3 to the 4th is 81, so this is certainly not true for n much smaller than 7. Just to show you the breadth of the areas where induction can show up, let's next go ahead and prove that for all positive integers, this integer 11 to the n minus 6 happens to be divisible by 5. So as expected, we're going to proceed by induction, so we're going to need to lay out a base case. The base case here is that for n equals 1, I get 11 to the first minus 6, which is 5, is divisible by 5. Big check mark there. Okay, 5 is divisible by 5. Perfect. So then let's see what the inductive step looks like. And so here would be an excellent place for you to pause the video and practice. Write down what the inductive step is supposed to say in this case. Okay, so here's our inductive step. If I start with a positive integer k, and it happens that 11 to the k minus 6 is divisible by 5, who knows, maybe it'll happen, maybe it won't, then so is 11k plus 1 minus 6. I want to make a brief pause here to note that this is one of the times where we really benefit from this weird choice that we made all the way back at the beginning of the class, that if you ever have an implication, then if it just so happens to be the case that the p part is false, well, then the whole implication is just true automatically and you don't have to think about it. So really what this statement is saying, and what every inductive steps statement is saying, is just as soon as it happens that this thing is true, and we have no reason from the inductive step alone to suspect it's ever true, but if it does happen, by chance, that this is true for a particular k, then it's automatically true for the next k. That's all the inductive step is ever saying. And again, in isolation, that doesn't do any good. It only does good for us when it's combined with the base case, which in fact says, hey, you know what, this thing that I had no reason to suspect ever happens? Well, it does actually happen. Here's the time it happens. And then that's sort of dropped in your lap, and then that gives you all of the subsequent times that it happens by putting these two pieces together. So let's prove the inductive step. So, as you're probably expecting, we're going to suppose that k is a positive integer, and 11 to the k minus 6 is divisible by 5. I'm going to write out what that means, which is that there exists an integer L such that 11 to the k minus 6 is 5L. And now I have to think about this 11 to the k plus 1 minus 6. And, how am I going to get the 11 to the k plus 1 minus 6 to relate back to the 11 to the k minus 6? Well, you guessed it. If I'm not sure, I'm going to pull out scratch paper and look at what happens. So I know 11 to the k minus 6 is 5 times L. And I want to look at 11 to the k plus 1 minus 6. Well, if I think back to what we did in the previous example, we can rewrite 11 to the k plus 1 as 11 to the k times 11. And actually, if I look at this actually also says that 11 to the k is actually 5L plus 6. So I could substitute that into here, which is to say that this is going to be 11 times 5L plus 6 minus 6, which is then going to be 55L plus 66 minus 6, okay, which will be 55L plus 60. And now that is divisible by 5. Again, it helps to work through this before you try to write up how to work through this. So here's writing up what we just did, but I want to make a couple notes about how we wrote this up. First of all, it really helps to tell the reader, I'm going to use this thing before you do it. So in this case, because I was going to mentally rewrite this 11 to the k like this, I'm going to go ahead and call that out before I do this factorization, because it helps the reader sort of put together, okay, what's going on here is that the author is relating this fact, and so writing it up like this makes that clear. Another thing I often get asked is about how much algebra you need to show, and you'll see here I actually stripped out a couple of the steps when I rewrote this, because you don't need to show every single piece of algebra. I would not really show less than this, probably. I think every step here is important, but you can certainly skip the intervening steps. And then, just like in all our proofs about divisibility or multiples or whatever, we go ahead and write down something, in this case I'm calling it m, such that this thing ends up being equal to 5m, and so then that proves that this thing's a multiple of 5. One particular character you'll see a lot during proofs by induction, just in examples and so on, is the Fibonacci numbers. And so I want to remind you what those are. So the Fibonacci numbers are this sequence 1, 1, 2, 3, 5, 8, where each number in the sequence is the sum of the previous two. Except for the first two, we have to sort of agree that the first two are either 1 and 1 or 0 and 1, and I'll talk about that exact mess in a second. I should also note that Fibonacci got these numbers named after him because he mentioned them briefly in a book that he wrote in 1202. Fibonacci was very far from the first person to talk about these numbers, and we at least have evidence that people talked about these numbers in this sequence as far back as 200 BCE, and so Fibonacci really only gets credit for these because Europeans were writing about them and Fibonacci was European, whereas Pingala, who wrote about them in the 2nd, 3rd century BCE, was living in the Middle East at the time. So, these numbers you've probably seen before, and you've probably played with them in all sorts of capacities. Usually they're going to be written with subscripts, so we'll write F1 for the first Fibonacci number, and F2 for the second Fibonacci number, and F3 for the third Fibonacci number, and so on. And so by this, it would look like, okay, F1 is 1, F2 is 1, F3 is 2, and so on down the line. And once you've written down an indexing like this, then this statement where each number is the sum of the previous two that is actually quite informal to include in a definition can actually be written as something like this. So why didn't I just write it down that way in the definition? Well, the reason for that is that there are two things that people disagree about when they're talking about the Fibonacci numbers. And so the first is, what is the first Fibonacci number? a lot of people will write it like this. So the first will be 1, then 2, then 3, and so on. But a lot of people will want to append a 0 at the front here. So 0 and 1 will be the first two that you define, and then each one after that will be the sum of the previous two. Which is all well and good and changes basically nothing, except that it changes the index. Because if you start with 0 and you call this F1, now this is F2, this is F3, and so on. But we have an additional problem, which is that people disagree on what you should label the first thing in a list. And so you may be thinking, well, this is absurd. Why is there any debate about this? But if you've ever done any computer programming in something like Python or whatever, you might notice that computer scientists vastly prefer to start counting at 0. And so to someone who is computer science oriented, they will want to in fact call the first thing in the Fibonacci numbers f sub 0. Now, you're probably tempted to say, well, that's just crazy. Why would we start counting at 0, and also aren't we mathematicians in this class, so can't we just start counting at 1 or whatever? But I would encourage you to actually adopt the view that sometimes it's nicer to start counting at 1, and sometimes it's nicer to start counting at 0, and you should actually choose to start counting at wherever makes things come out nicer. And so the numbers themselves, the Fibonacci numbers, are never going to change. But these subscripts that they're attached to will. And anytime someone's talking about this with the Fibonacci numbers or any other sequence, they're going to be talking about the phrase indexing. And so indexing is really the question of where do you start counting, what subscript, and where do you start in the sequence. So, just to make this clear, I gave you two questions that people disagree on. Namely, whether you start at 0 or 1, so these two are the people who start at 0, these are the two people who start at 1 in terms of what the first Fibonacci number is. And then whether you start labeling your list at 1, like these two do, or at 0, like these two do. And so what's the upshot of this? The upshot of this is that there are 4 different ways to define the same sequence of numbers. And so if someone says, what's the 7th Fibonacci number? There's not really a well-defined answer to that. You really have to ask them, okay, well, how did you index it? As a result, every time in a homework question or test question or whatever, when I say anything about the Fibonacci numbers, I'll always tell you how I'm indexing them in that particular instance. And it might be any of these, and you'll really see all of these pop up in the real world when people talk about the Fibonacci numbers. So just be aware, anytime you have a sequence, you're going to start seeing this kind of thing. And if you happen to take linear algebra last semester, then you might have seen that people do this with vectors too, or matrices. What's the upper left entry of a matrix? Is it the 1, 1 entry, or is it the 0, 0 entry? And so on and so forth. And really, rather than picking a side, I again encourage you to just take the philosophy, I'm just going to roll with whatever people use and pick up for myself whatever I think works most naturally and nicely in a particular instance. So by way of modeling that for you, I'm going to do a question about the Fibonacci numbers. And I'll start by just telling you that for this example, I specifically want to think about them indexed this way. This is a style of induction question you'll often see, and I think these are the most fun types. They'll give you something, and then they'll say, guess and prove a formula for it. So, how do you guess the formula? Well, in order to guess the formula, you have to write down enough data to figure out what the formula probably is. So, if I write down f1, well, that's just 1. If I write down f1 plus f3, that is 3. If I write down f1 plus f3 plus f5, that is 8. And if I go all the way up to f9, that is 55. Now, one hopes that anytime someone asks you to guess and prove a formula for something, if you collect, say, this much data, it won't be that hard to guess what the formula is. And so you see, okay, hey, this 55 is that 55. This 21 is that 21. This 8 is that 8. 3 is that 3. So this one must be this one. And so then we can make a guess. And so the fancy math word for a guess is a conjecture. Our conjecture is that if you sum the first n odd Fibonacci numbers, then you get... And so here's where we have to pay close attention to the indexing. When I added up through F7, I ended up getting F8. So that must mean I'm guessing that this is F sub 2n. Now, I certainly don't have anywhere near enough data to claim that I've proven this statement. If anything, the paper that we read, Law of Small Numbers, should be enough to dissuade you from thinking that because something happened to work 5 times, that means it works forever. But we do have a tool at our disposal that will hopefully let us prove this. Namely, of course, induction. What does our base case say? Our base case says F1 equals F2, which, by this choice of indexing for the Fibonacci numbers, is true. Then what does our inductive step say? It says that if for a positive integer k, it just so happens that this thing works out, then it also works the next time. Apologies, that got a bit messy, but this should say if, just literally this thing with k's, then the sum of the first Fibonacci number up to the 2k plus 1 minus 1th Fibonacci number is the 2k plus 2th Fibonacci number. 2k plus 2 just being 2 times k plus 1. Okay, so let's suppose that this thing is true. And now we want to consider the second piece. And now, as before, I'm going to rewrite this so that I can use the thing I've assumed I know something about. Namely, I'm going to back this pattern up 1 and think what was the odd number before 2k plus 1? It was 2k minus 1. And so by our assumption, this sum of the odd-numbered Fibonacci numbers up to 2k minus 1 is the 2k Fibonacci number. But, beautifully, what do you get if you add the 2k Fibonacci number to the 2k plus first Fibonacci number? Well, these are consecutive Fibonacci numbers, so if you add them together, you just, by the definition of Fibonacci numbers, get the next one, which is f sub 2k plus 2. And that just so happens to be the thing we are trying to prove. So that proves the inductive step, which completes our proof by induction, which turns our conjecture into a proposition. I want to make one editorial note of one thing I would revise if I was rewriting this proof to make it read a little bit more cleanly, which is that the very first time I talked about this, I wrote f1 plus f3 plus ... plus f sub 2n minus 1. The pattern here is pretty clear. Namely, I'm saying, okay, add together the first n odd Fibonacci numbers. But every time after that, I wrote it like this. And that did make the writing look cleaner, but no one who looks at this is going to rightly interpret that the thing it means is the sum of the odd Fibonacci numbers. They're going to assume this ... is plus f2, plus f3, plus f4, plus f5, and so on. And I only noticed I was doing that sort of towards the end here. And so again, if I were typing this up or if I were proofreading this, I would definitely fix that and I would put a plus F3 every time one of these showed up, just so that someone who was looking at this would know exactly what was intended. I'm going to do one more example in this video, and then in the next video, I'll do some weirder examples of induction, where you have to shake up the model for induction more than we have had to in the examples in this video. This question concerns tiling. What is tiling? Tiling is something that shows up a lot in combinatorics, where you're given a chessboard, say, and you're given some sort of shape, like sometimes it's a domino, or in this example, it's going to be a triamino that looks like that. And you're asked basically to cover the board in them. So, for example, if I were to try and cover this board in dominoes, I could do it something like... Oh, that doesn't work. Because I missed this square, and I missed this square, and so this is not a tiling. But let's see, I bet I could do better. Let's see, I think I was okay up till there. But then I think I was supposed to do that. So this is a tiling of a 4x4 chessboard by dominoes. So here's a somewhat classic question, just to give you an example and show you that some interesting math happens when you talk about these things. Let's take our friend the 8x8 chessboard. And all I'm going to do to this chessboard is I'm going to knock off the corners. So there's a bunch of chessboard in the middle. I'm not going to attempt to draw it. But I'm going to remove that and that. So this isn't an induction question, but it's a good warm-up to think about the induction question we're about to think about, which is, can this board that remains be covered by dominoes? So there's some basic sanity check things you might check, like that the original chessboard had 64 squares, so this has 62 squares. So by virtue of the fact that it has 62 squares, you might be quite inclined to believe that it's possible I could just take 31 dominoes and just sort of lay them out. Although I showed you that you have to be a little bit careful at least, because if you just do it kind of randomly like I was doing over here, you can accidentally end up screwing up and finding that you can't finish your tiling, even though if you'd done it smarter, you would have been able to. So just to give you a visual, here's someone who has tiled the entire 8x8 chessboard with dominoes. This is almost what we want, but we want to know if we could still do this if I knocked off the two corners that I indicated before. Here's the visualization of that is also instructive. Namely, the added thing here that wasn't in my terrible hand drawing is the checkerboarding. Namely, half the squares are black, half the squares are white. And the thing that this picture makes clear is that when you perform the procedure that I outlined where you remove the two corner squares, the two squares you've removed are both white. Now, at first, your reaction to this might be, well, who cares? No one in the question asked anything about black squares or white squares, so why should it matter? But it turns out that even though the question doesn't mention the colors of the squares, the answer about whether you can tile the board or not hinges entirely on the colors of the squares you remove. In particular, I claim if you remove any two white squares from this board, it is impossible to cover it with dominoes. On the other hand, if you remove any white square and any black square, pick your favorite white square and black square, it will always be possible to cover this thing with dominoes. Half of that is not so difficult to explain. Namely, the half I'll explain to you is why any two white squares you remove make it impossible to cover the board with dominoes. And here's the thing about a domino. No matter how you lay this domino on this board, it will always cover a white square and a black square. Why is that? Well, the whole reason why checkerboards are checkerboarded is to make the lines between adjacent squares clear, so no two squares that are adjacent are the same color. That is, in fact, literally the reason why chessboards have this pattern. But what does a domino do? It covers two adjacent squares. And so they can't be the same color, so they have to be different colors, namely one of them has to be black and one of them has to be white. But if I look at what remains after I remove two white squares, I have 32 black squares and 30 white squares. That being because originally there were 64 total squares, half of which were white and half of which were black, which is 32 of each, but then I took away two white squares, so I'm left with 30 white squares and 32 black squares. But if every domino covers one white square and one black square, that math is not going to add up very well. In particular, it is impossible to put more than 30 dominoes on this board, because every domino needs to cover a white square, and there's only 30 white squares to go around. So, after you put down as many dominoes as you want, you'll get stuck at most 30 dominoes, and there will be 2 black squares staring back at you that are not covered. Really, this kind of question is at the heart of combinatorics, which is all about these sort of secret structures that underline these kinds of arrangements. Even though it seems plausible, like there doesn't seem to be any clear reason when you first look at it why you couldn't cover this thing with dominoes, once you look at it from the right way, it turns out there's this sort of secret structure. The coloring is there on the board, even if you don't see it, and even if it's not mentioned in the problem, and it dictates the entire behavior of all the questions of this sort. This was all a long-winded introduction, so that we could get to what is my favorite induction proof. So, here's the thing we're going to prove. We're going to prove that if you pick your favorite positive integer and make yourself a 2 to the n by 2 to the n chessboard, so for example, you could pick n equals 3 if you're boring, and that would give you an 8 by 8 chessboard. Or you could pick n equals 10, and then you'd get a much larger 1024 by 1024 chessboard. And the claim is that no matter which n you choose, and no matter which square you then remove from that board, as long as you remove exactly one square, then you can cover it by these things I've called bent triaminos. And what's a bent triamino? A bent triamino is, well, it's a domino with 3 pieces, but the bent part tells me that it makes this 90-degree turn rather than just being 3 in a row. So when I talk about triamino tilings, this is the kind of thing I have in mind. I do want to make one note, though, that in this image, the triamino tiling we're looking at is actually a triamino tiling of a 9 by 9 board. So this is like a Sudoku grid. It's got 81 squares on it, rather than the typical chessboard, which would be 8 by 8. And in particular, this definitely is not a power of 2 by a power of 2, which is the kind we actually want to consider for this problem. Here's an example of the kind of tiling I actually want to talk about in this question. Here we have a board that is 32 by 32, and it has been tiled with triaminos. Except, if you look very, very closely at this board, you will see that there's one tiny tile on this 32 by 32 gigantic board that has not been covered. 32, notice, is a power of 2. It's 2 to the 5th. So the claim in this question is that if you take any board like this, 32 by 32, 64 by 64, or whatever, remove any one square that you want, so you could remove that one, but you could equally well remove any of the other squares here, then what's left can always be covered by these sorts of triaminos. So we've got our work cut out for ourselves. Let's try and prove this. So, as you expect, we're going to do this by induction. Now, there's a lot of numbers you see in this question. So there's the n's, but there's also the powers of 2. And so you might think, okay, how exactly are we going to do our induction? But the n we're going to use for induction is, in fact, the thing I called n in the question. And if you want to emphasize to the reader sort of like what the thing you're laying out on the lily pads for the frog to hop along is, you can just say on that variable. So that, in this case, is why I said we're proceeding by induction on n. So what's our base case? Our base case is n equals 1. And so I need to show that if I take a 2 by 2 board, right, because if n is 1, 2 to the n is 2. So these are very little boards. And I need to show that no matter which square I happen to remove, I will always be able to cover this with triaminos. So I could remove that square, or that square, or that square, or that square. And it's not so hard to see how I'm going to go about covering these things with triaminos. Namely, like that, like that, like that, and like that. Note, I definitely need to remove a square. If I didn't remove a square, well, there would be 4 squares to cover, and I can only cover them in sets of 3. That's definitely not going to happen. So this is what the inductive step says. If k is a positive integer, and it happens that I can tile all 2 to the k by 2 to the k chessboards with these bent triaminos, as long as I remove one square, then the same is true for 2 to the k plus 1 by 2 to the k plus 1 boards. And I want to draw attention to and emphasize this word all, because I actually, in order for this induction to work, I need to show that this works no matter which square is removed. I can't just show there's some particular square I can remove that makes this true. I need to show that actually this is true no matter which square I remove. So I'm going to suppose the inductive hypothesis is true for 2 to the k by 2 to the k boards. Okay, which is just saying I'm assuming that all 2 to the k by 2 to the k boards with one square removed can be tiled by bent triaminos. And then I'm going to consider a 2 to the k plus 1 by 2 to the k plus 1 board. Okay, so this side is 2 to the k plus 1, this side is 2 to the k plus 1. And here I'm going to make a clever observation, which is that 2 to the k plus 1 is 2 to the k plus 2 to the k. So I could split this in half. And, well, since this 2 to the k plus 1 is 2 to the k plus 2 to the k, so is this one. So I can split this in half as well. And so what I've done here is I've split my 2 to the k plus 1 by 2 to the k plus 1 board into 4 2 to the k by 2 to the k boards. Now think about for a second, why is that a good idea? And the reason why that's a good idea is that the only thing we get to assume in our inductive hypothesis is something about 2 to the k by 2 to the k boards. And so, unless I can make a 2 to the k by 2 to the k board appear, then I can't use the inductive hypothesis, and there's no way I can possibly prove this. But we don't have that problem. We have our 4 2 to the k by 2 to the k boards. Now remember, we don't get a choice about what square we remove, but we have to remove a square. And so that's what I'm emphasizing here with an arbitrary square. I can't say, like, knock off the one in this corner. I need to prove this no matter which square I happen to have removed. Now, here I'm going to use the magic of without loss of generality that I've mentioned before, and I'm going to say that the square I removed is in the upper right board. So somewhere in here, there's a single square missing. So these two things might seem in contradiction. On the first thing, I'm emphasizing that the square needs to be arbitrary, but then I'm also saying, well, it's arbitrary, but I'm going to put it up here. But what I'm saying is, you pick any square you want. It doesn't have to be in this square. You can pick one there, pick one there, pick one there. But this question doesn't really care which way I look at the board. So if you pick a square here, I'm just going to turn the board 90 degrees counterclockwise. Or if you pick a square here, I'm just going to turn the board 180 degrees. And so, even if you pick a square that's not in this corner, because of the symmetry of the problem, I can always put it back in this corner. Hopefully that makes sense. Now we get to use our inductive hypothesis, which says that all 2 to the k by 2 to the k boards with one square removed can be tiled. Now I have one of those, namely this thing in the upper right. And so this piece, this gets tiled by the inductive hypothesis. It's a 2 to the k by 2 to the k board with one square removed, so by assumption, all of those we know how to tile. That leaves us with a substantial problem, though, which is that I have 3 2 to the k by 2 to the k boards, and so I'm tempted to say that by the inductive hypothesis I can tile those too, except I can't, because these actually don't have a square removed. But, and here is the genius part of this proof that makes this my favorite induction proof. I can put a single triamino here right at the corner. And what putting a single triamino here at the corner does is to remove one square from this 2 to the k by 2 to the k board, one square from this 2 to the k by 2 to the k board, and one square from this 2 to the k by 2 to the k board. In this case, by remove, I happen to mean cover with a piece of triamino, but that's as good as removing it. I only need to cover everything but that one square. And so this one triamino I'm placing is a choice. I'm choosing to put it there. And now here's where it's very easy to get lost in the weeds of thinking about exactly what this question is saying. So I want to go over this again. At the end of the day, the thing we're proving here is really a for every there exists statement. For every 2 to the n by 2 to the n board with one square removed, there exists a tiling. And so I can't prove that outer for every by example. It's a for every statement. For every statements don't work like that. But I can prove that inner there exists by example. And so when I'm making this choice, what I'm doing is I'm showing you there is an example of a way I can tile this board. And one of those examples has this triamino put here. And once I've done that, this board, and this board all get tiled by the inductive hypothesis. And so then, as soon as I realize that if I've tiled each of these 4 boards separately, that means I've tiled them collectively, we've actually proven what we wanted, which is that this 2 to the k plus 1 by 2 to the k plus 1 board in its entirety can be tiled by these bent triaminos. Anyway, I hope you appreciate this proof. I really like it. Either way, that's all for today. I'll do more examples next time, but we've earned a break. So I'll see you next time.